Okay. Any question from this hand? If you have question from midterm, maybe you should hold off because I haven't graded it. So let's discuss midterm maybe on Thursday or next Monday. I guess if you have really urgent question on midterm, you can ask right now. We will discuss midterm on hopefully Thursday where we can get it graded. Okay. But if you have question for how do I things before midterm, you can ask right now. Why did I? Let's see. It's this, right? Why isn't this? Oh, is this broken? Shit. Oh, okay, here it is. Yeah. So before we talk about midterm, let's have this filler chapter. This is something we I guess skipped before we go to midterm. And this is a quite interesting concept. It's about classical versus quantum correlation. Okay. So yeah, let's talk about this thing that we skipped at chapter 2.6. And okay, so what's the deal here? And yeah, so we want to talk about entanglement. So recall that we have those entangled states we have learned a lot. This EPR pair that is beta 00 equal to 1 over square root 2 00 plus 1y. We use this a lot. We use it in teleportation and we use it in superdense coding. And it's one of the 4 Bell states. And actually, for historical reason, people actually call EPR pair the other one of the other Bell states as the EPR pair is 1 over square root 2 0 1 minus 1 0. And that's the notation the textbook use. And that's because historically, so EPR are Einstein, Polonsky, and Rosen. When they write their paper, they actually use this state. But that's not very important here. Anyway, so we'll use this beta 00 as our entangled state throughout today. And yeah, let's talk about classical and quantum correlation. So we say Alice and Bob have quantum correlation when they share this entangled state beta 00. So Alice has beta 00 and Alice and Bob, and Alice has this, the first part is 0 1 and Bob has this 0 1. Okay. And well, people will say you measure this beta 00 so Alice measure this beta 0, let's say measuring z basis. Then Bob will have this phase and speed of light collapse of the state, right? And that's really weird. So that's like when Alice measure in z basis, and Alice will get 0, and instantaneously Bob's state will also collapse into 0, even though Alice and Bob may be physically really far away. Right. So this is one of the weird part of our quantum mechanics that Einstein doesn't like. That is phase and speed of light collapse of state. What this is really weird. Okay, so Alice gets 0, Bob's state will immediately become 0, and Alice gets 1, Bob's state will immediately become 1. But and this is the popular science description you will see on the entanglement. But is this really a weird thing where Alice gets 0 immediately you know Bob will get 0, but Alice gets 1 immediately you know Bob gets 1? It's not quite right. And that's because you can get this 0 0 and 1 1 correlation by just doing classical shared randomness. So yeah. So think about we can get the same effect if we just have someone flip a coin, right? It's kind of doing lottery number. Okay, let's say this is flip coin. So you can have some referee flip a fair coin as head with 50%, a tail with 50%, right? And write down the result as some number S. And the referee can write down this S and write this S in 2 sealed envelope, right? And send those envelopes to Alice and Bob. And Alice can open her envelope and see, oh, the referee got the coin result as 0. Then she know Bob also have the 0 result envelope, right? And if Alice see a 1 on her envelope, then she know Bob also has a 1 on the envelope. So really this 0 and 1 sharedness is nothing quantum. You can get the same result by just doing this very classical protocol, right? Where you have someone doing this just classical randomness. You can flip a coin, throw a dice, etc. And you write down the result, put it in envelope, and share them to Alice and Bob. Then Alice and Bob will have this 0, 0, 1 correlation. Okay. And so now there is this question. So physics like to ask, is quantum mechanics just a lot of shared randomness, right? Can you just can you just get all the quantum effect with a lot of shared randomness like this, Alice and Bob? And in one physics term, it's called local hidden variable model. And well, we already talked about a lot of quantum mechanics, so we kind of know this is not true, right? Because we have seen like the algorithm where you have quantum speed up, right? Like Diels-Josa and the Simon's algorithm. But here we will see a quantum advantage in another way, where you have this correlation between two far away parties that's only possible through quantum mechanics. So yeah, so I go ahead a little bit where I answer the question. And yeah, so here we are going to see that there is a quantum advantage in just using EPR pair. Although we say measuring the EPR pair, so if Alice and Bob measure this EPR pair both in Z basis, then there's nothing they cannot get just from classical effect, right? Because they will get a distribution that's both of them are 0 or both of them get 1, 50-50. But we say you can get the same distribution by just having shared randomness. But we are going to see that using EPR pair, they can get some kind of correlation that's impossible to get with just classical shared randomness. Okay. And that's the quantum correlation. And the key to do it here is to choose a smart basis or choose a lot of smart bases such that the measurement Alice do and the measurement Bob do will have interesting correlations. Okay. And the question so far? Do people understand why this is classical correlation? Okay, there are some not. Okay. And so here then we diverge from how the book talk about it. So it's really interesting to see how the book talk about it in more physicist way, where they have the what's that called? Anyway, there's some the built-in inequality. They are going to calculate some quantity that the quantum correlation will give you violation on classical bound. But anyway, here we're talking a more CS perspective, where we are going to play this non-local game CHSH. Okay. And yeah, it's going to be very operational. Alice and Bob with the shared entanglement is going to play again, and they will have winning probability higher than what's possible classically. And as we say, yeah, Alice and Bob, they are using the shared entanglement, can get more correlation than just shared randomness. And this is going to be by a non-local gain. And what do we mean by a non-local gain? There are lots of formulation, but the thing we do here is so I guess there are really 3 players. So there is Alice and Bob, and there is a referee. Okay. So this referee is not quite a player. So it's going to be Alice and Bob, and there is going to be someone that's a referee, and the referee is someone that will set up the game and just judge how Alice and Bob do in their game. So referee is not really a player because the referee don't have a strategy. You just follow a rule and set up the game. And Alice and Bob are players. So Alice and Bob have a strategy. And in the setting here, so Alice and Bob are not playing against each other. So they collaborate together and they want to win together. Okay. So they will choose and think about strategy beforehand and try to set up the strategy such that they play under the referee's rule and win with the highest probability. Okay. And as we said, the win will be output something accepted by a referee. And the interesting part here is this non-local. Okay? Non-local gain. So what do we mean by non-local? We need to first guess what's local. And well, what's local we kind of already see, right? This is kind of like in the super dense coding or teleportation model. So Alice and Bob, we just think they are physically far away. And so there will be actually no communication between them at all. Okay. So no communication. Yeah. And the only correlation they have is, well, if they are classical, they have some shared randomness, like just pre-shared beforehand, or they have some entanglement they pre-shared beforehand. Okay. So yeah, that's what's local. So Alice needs to do her things on her local side, and Bob needs to do his thing on his local side, and there is no communication between them. So so they have their locality on each side, and it is a non-local game because they are two local parts. Sounds weird when you say like that, but makes sense, right? Non-local game means there are two local parts. Okay. Anyway, I guess it's non-local because they share entanglement. Anyway, so as we said, Alice and Bob cannot communicate with each other. That's important. But and as we also said, they can coordinate a strategy beforehand. So yeah. So Alice knows what Bob will do, and Bob knows what Alice will do because they collaborate with each other. And the non-local part is they can share randomness or entanglement. Okay? I guess let's see it again. So here's again CHSH. So Alice and Bob, they will share entanglement or share randomness, and there is a referee. And the referee will send one input to Alice and one input to Bob. So referee will send one bit X, that's 0 to 1 with 50-50% probability, and one bit Y to Bob, and it's also 50-50, and those 50-50 are independent. And Alice and Bob need to So Alice need to output 1 bit A, and Bob need to output 1 bit B. And the referee will get C this is A and C this is B. And the referee will determine that Alice and Bob win. And well, there are 4 bits here, right? So there are X, Y, A, B. So there are 16 probability of those things. But anyway, so out of those 4 variables, the referee will declare win or lose by doing this calculation. So is X times Y equal to A O plus B. So this is A and A, X or B, basically. And so referee will check this. And this equation is true, then Alice and Bob win. Okay. And so let's again. But before we go into detail, let's talk a little more about its name. Okay. We are really going really fast. Okay. We might stop the class very early. Anyway, so CHSH again. So CHSH. And actually stands for 4 physicists. So Clauser, Horner, Symphony, and Holt. And they are a bit more famous now because just this year's Nobel Prize is granted to basically experiments that related to the CHSH gain and the Bell's inequality. And in particular, this Clauser gets 1/3 of the Nobel Prize, and for the experiment on this again, okay. And for some gossip on other people, and unfortunately this is dead, and this is dead, and I believe he is not doing physics, so that's that. Yeah, you need to live long enough to get a Nobel Prize, but heck, Clauser get a Nobel Prize, so that's really cool. Okay. And okay, so let's back into the more mathematical part. Yeah, so this is again Alice and Bob, and Alice received. So let's look at this once again. So if we lose people here, it's kind of hard to get on because all the analyses are going to build around this. So Alice gets X as input, and Bob gets Y as input. X and Y are 1 bit. And they are drawn totally uniform. And Alice basically only see. So what will Alice do? So Alice will see X, and Alice can also do something with entanglement or Schön rings. And whatever she sees here, she will use that to determine A as her output. And Bob will also see this Y, and Bob will also do something. So Bob will do some function on this Y and her part of entanglement. Sorry, his part of entanglement or Schön rings, and Bob will do this on B. Okay, and and the hard part of this is, I guess, just like the communication things. So Alice and Bob want to have their output kind of correlated with this X and Y. So they want X or B equal to X times Y. But the thing is, Alice doesn't know Y, right? So they have no communication, so Alice doesn't get to know Y, and Bob doesn't know to get to know X. So none of them are really going to know this X dot Y. Okay, and so the hard part is how do I get something, get up some correlation between A and B that have this weird correlation on X dot Y. Okay, and yeah, and as we said, and X and Y are handled uniformly random, so it's a 1/4 probability for any 4 of the outcome, and and after Alice and Bob output is A and B, so these A and B are really sent back to a referee, and the referee obviously knows X and Y, and he will check A and B. Okay. And this is there's a little more generalization on this. So this kind of gain is called XOR gain, just because the winning condition is determined by the XOR of Alice and Bob's output, and that's just something theoretical that people study. But anyway, and so this looks a bit more scary, and let's draw this into a table. Yeah. So what the referee want to happen basically like this. So we list the input to Alice and Bob, so X and Y. So obviously X has two choices, Y has two choices, and there are totally four choices. And out of those four choices, then X dot Y will determine what the A plus B equal to, right? And okay, we will be here. X dot Y should equal to A plus B. So, and X dot Y is equal to, well, you can just do the multiplication. So it's 0, 0, 0, 1, right? And we've seen this XOR thing, that A XOR B equal to 0 means A equal to B. And so that means on those three possibility, A should equal to B. And on this possibility, then A needs to be not equal to B. Okay? So this is a bit more organized representation of Alice and Bob's winning condition. So they should output the same thing if X, Y equal to those three possibility, and they need to output a different thing when X and Y are both 1. Okay. So anyone want to give me a classical strategy for doing this? What's the way to do this classically? Okay. Okay. And from here, you can see, and yeah, Alice and Bob want to set up a strategy to output A and B, such that optimize this. And there is a classical strategy that win with 75 possibility. Maybe that is easier. Okay, we'll receive the answer. Yeah. And well, they have a way to do 75% probability, and that is they just ditch this block, right? Because you see those three blocks have the same thing. Right, so they will just ditch this block and try to win when X, Y equal to these three possibilities. So 0, 0, 1, 0, and 0, 1. So they don't care about what's X and Y. They just always output A equal to B. So let's say they always output A equal to 0, B equal to 0. Then they will win with 75% probability because because the referee always do the same thing. The referee hand out X, Y uniformly. So with 75% probability, they are going to hit one of those three blocks and they win. Okay? That's a very trivial strategy. Always output A, B equal to 0, 0. And okay, now we have, okay, now we are going to hand wavy prove that actually this is the best possible thing you can do classically. Yeah. And so we need to, so there are three levels of classical strategy. Okay? So before we talk about this is optimal of classical, we need to be a bit more precise about what do we mean by classical strategy. So there is a worst kind of classical strategy where Alice and Bob don't even share randomness, so they just act independently. And they actually also don't have randomness, so they just run deterministic strategy. That's a classical strategy. And in that case, then Alice output A will just be a function of her input X, and Bob's output B will just be a function of input Y. And then there will be randomized strategy where, but also this is also when Alice and Bob don't have correlation. So Alice can do some randomized strategy, and Bob can do some randomized strategy. And Alice's randomized strategy will depend on some random seed S1, and Bob's randomized strategy depends on some random seed S2, and S1 and S2 are independent. And finally, Alice and Bob can share randomness, as we say. So Alice and Bob will do some strategy and random strategy, and they have this random seed that's shared. But anyway, and so the proof kind of goes from this level up. And first, you can easily see that for deterministic strategy, this 75% thing is optimal, because you just look at the blocks and you realize there's no way you can win all four of them with a deterministic strategy. It's pretty easy to see. So yeah, so there is no way to win all four of them, and well, then the next best thing is win 3 of them, and we have a way to win 3 of them, and so that's the best. And yeah, for deterministic strategy, you either win a block or lose a block. Okay, so deterministic strategy, this 75% is optimal, and and you can also do even number proof, that is the number of deterministic strategy is just countable. You just say what does Alice do when he see x equal to 0, and what does she do when see x equal to 1, etc. And there are only 2 to 4 possible strategy, and you list all of them, and you see this 75% is the optimal one. Okay, so deterministic strategy is pretty easy. And now we'll hand wavy give you a hand wavy proof why this is also optimal for shared random strategy, and that's just because every random strategy is actually a linear combination of deterministic strategy. Okay. And so you think about random strategy where you can fix these random seeds, right? So when you fix the random seed, then Alice and Bob are basically running on a deterministic strategy. And the winning probability was going to be the probability of is going to be just the probability mixture of what you do condition on your winning random seed is something times the probability of your random seed. So then this part is the deterministic strategy, right? This is a winning probability of your strategy condition having some random seed days. But we already said all the deterministic strategy must have the maximum winning probability 75%. And you do a probability mixture of a whole bunch of things that's less than 75%. You are going to get something less than 75%. Okay. So shared randomness don't really help you, and yeah. So for all 3 of them, the best possible thing you can do give you a 75% winning probability. Okay. So that's the classical part. Any question? No? Okay, now we have 20 minutes. Hopefully you are still awake enough. So we're going to see the interesting part of this lecture, that how do we win more than 75% with shared entanglement. Okay. So actually you are going to win something about 85%, not exactly 85%. Okay. And that will violate built-in inequality or in some form. And once again, or again, look at this. Okay. And before, okay, so the optimal strategy is 1 page here, but we should scroll down a little bit for this property. Okay. So okay. So the property here, this is the important thing. And this is a generalization of the thing we talked about very beginning. So let's do this. Quite okay. So at the very beginning, we say that, well, if L is measured in Z basis and then Bob state will also get projected to this Z basis state, right? So L is measured in Z basis and L is get this 0, then Bob state will also become 0. And L is get 1 and Bob state will actually become 1. And this is actually true for more bases. So Alice can measure in a whole bunch of different bases and get the same result. So the requirement here is a bit weird. So Alice need to measure in a basis that's real. Then Bob state will collapse into the same thing. Okay, so let's see that in in the equation here. Okay, so suppose Alice measure, so we don't know the real thing yet. So suppose one of the basis state Alice measure is this psi, and it's a qubit, so qubit state, so that's on A0 plus B1. And let's just see what happens when Alice project her part into psi. So we apply this psi projection on Alice part, and as indicated by the tensor product thing. Sorry. How we think about tensor product. So Alice do this projector on her part, and nothing happened on Bob's part, so we just tensor its identity. Then we apply this on our EPR pair beta 0, 0. Okay. Then what happened? So this psi projector is K psi plus psi, and we can keep it K psi because we know this is what Alice is going to get on her part. So we have this K psi, and we separate into this weird thing. So this not quite balanced thing. So on Alice's part, we have this broad psi, and we write out this broad psi as A star and 0 ket and B star 1 ket. Then we have tensor identity, then we multiply this to our EPR pair. So this is something that you probably see in your midterm, right? So this not quite is a bit mismatched thing. But anyway, these two things together should give you a state on Bob's part, because the Alice part will do some inner product between those broad and ket and become a number. And then we see what happened. So this 1 over square root 2 is a number, so we can just pull it out. So it's a 1 over square root 2 here. And then we do the multiplication one by one, right? So then, so the distributed law. And so let's see. So A star 0 tensor I multiplied on C. Then 0 inner product with 0 is 1, and it will pick out this 0 here. So A star 0 I on 0, 0 give you this A star 0, and A star 0 I on this 1, 1, because 0 and 1 are orthogonal, that will give you nothing. And similarly, this B star 1 on 1, 1. B star 1 0, 0 will give you nothing because 1 and 0 are orthogonal, and B star 1 1, 1 give you this B star 1. Okay, and so we are in this nice form. So if Alice project her part onto this psi state, so basically her make a measurement, and when she hits this measurement operator of projection onto psi, then her part will get into psi as expected, and the Bob state is going to be 1 over square root 2, and A star 0 plus B star 1. Okay, and then okay. Then we see that this A star 0 and B star 1 looks really like this A0 plus B1. except we have this weird star here. And that's why we want psi to be real. And for psi to be real, we just means this A and B is real. This is basis dependent, but well, that's that. And yeah, so if A and B is real, so that's what we mean by psi is real, then this is also psi. So the whole state is 1 over square root 2 psi tensor psi. Okay. And this is what we want. So Alice make this real measurement, she got psi, and Bob will also get psi. And there is this weird 1 over square root 2, and that just means the state is subnormalized, as we keep saying. So this means this measurement will succeed with some probability 50%. Okay. But the thing we really want to see here is we get this psi tensor psi. So whenever Alice do her measurement and Alice do some basis measurement and her part and the basic state is real, then that will project this entangled state, the bar part of the entangled state, to the same state. Okay. So for example, just once again, for example, if this psi is 0, then Bob will also get 0. And if this psi is 1, then Bob will also get 1. And so this generalizes the fact that Alice and Bob both measure in Z basis, they get 0, 0, and 1, 1. And also, for example, if Alice measure in a plus minus basis, they are also real. And then Bob will also get plus minus. Okay. And you can even check that plus. So the plus tensor plus and minus 10 plus minus tensor minus is the same as this beta 0, 0. Well, plus you also need 1 over square root 2. So, okay. So this beta 0, 0 is kind of basis independent. You can look at them at all the real bases, and it will look at 0, 0 plus 1, 1. Okay. This is any questions, because that's this is fundamental of what we are going to do next. And so what we are going to do next, knowing this, is Alice and Bob are going to pick 2 bases each that are mismatched, but give them good correlation. And well, I don't really have a good derivation, although you can kind of take a good guess by yourself. But here is what people figure out. So yeah, so this is the basis Alice pick, and this is the basis Bob pick. So Alice need to pick 2 bases, because remember Alice has 2 input. So when Alice input is 0, then she picks this plus and minus basis. And when Alice input is 1, then she picks this 0 and 1 basis. So one thing first is that, okay, so this is a bit confusing. And remember, this is not a slice or block sphere. Okay, so hopefully it's not too confusing. Yeah, remember in block sphere you have like this 0 and 1 on the z-axis. So no, so here we are actually respecting the angle between the state. So 0 and 1 are actually a signal in our picture. Okay, and we are drawing all. So we are drawing all the real linear combination of 0 and 1, right? Because you only care about real state. Okay. So we are drawing this 2D surface that spanned by 0 and 1, and with real coefficient. And remember, plus state is 0 plus 1, and the minus state is 0 minus 1. Okay. So this makes sense. And you might also see that we have this weird dashed line here. That's because, so at least make say it's 0 and 1. So at least make a measurement in 0 and 1. And, but we still need to say what's the output A and B, right? So one of them should correspond to A and one of them should correspond, so at least need to give output A. So A equals to 0 and 1, and there are two choices. And so this no dash thing means that if you see output measurement result 0, should output A equal to 0. And if you see this dash line, then this means A equal to 1. Okay, so understand this. No more dash notation. Okay, and yeah, so similarly Bob has two choices. So Bob, if his input y equals to 0, and then he chooses this golden pair. And if his input is y equal to 1, then he chooses this blue pair. And they are mismatched to those two things here. So you have this pi over 8 angle here, and then remember this angle is pi over 4. So it's kind of the middle of this thing. Okay. And 10 minutes it should be enough. Then we just going to see the magic happen. And a little spoiler is so this pi over 8 is going to give you our 85%, because cosine square pi over 8 is 85%. Okay, so let's check how this actually works. And probably the first one is most important. We'll set you up a nice example. Okay, so let's see what happens if let's clear this. So what happens when when so this should be x and y. Sorry about that, this is x and y. That's why it's confusing. So we need to consider our xy pair, right? And let's go back. Remember, xy pair, we have those four situations. So we have 0, 0, 0, 1, 1, 0. Those should have A roughly equal to B, and when xy equal to 1, 1, you should have A not equal to B. And so let's see what happens when xy equal to 0, 0. So xy equal to 0, 0, then it's this golden pair, right? And let's draw the bob thing up here. So it's a little easier. So Alice will measure in these spaces, and Bob will also measure in these spaces. And what happened? And that's why we have this thing. So Alice measure in these real bases. And let's say Alice get a measurement outcome 0. Right? And then the Bob thing says that when Alice measures this thing, then part of a state will also become this thing. Right? That's what we get here. And so Alice gets this plus state, and that will project Bob's side of the Bob's side of the entangled EPR pair also to this plus state. Then Bob will measure in this weird pi over 8 angle. And Bob wants to see, is this state close to this or close to that? And now this angle is pi over 8. So with our 85% probability, this is quite close to here, right? So with our 85% probability, Bob will also get this outcome. And so Alice measures 0, then 85% chance Bob also get 0. And we have a similar thing here. So if Alice measures this minus state, then that will project Bob's side, once again using this. that will project Bob's side of the entangled state into this minus state. And then Bob measure in his basis. And once again, you see 85% probability Bob get this measurement outcome. So Alice get measure 1, then Bob have 85% chance to measure 1. Any question? No? Okay. If you accept this, then the other thing we are just going to check that this construction work. We should be able to do in 5 minutes. Okay. So that's 0, 0. Then let's just check one by one. So 0, 0 and 0, 1. So Alice also do this. And what does Bob do? Okay, 1 is this. So Bob's 1 is this thing. Okay. Okay, so Alice measure in this 0 basis and Bob measure in this 1 basis. Okay, it looks far away, but actually not, because as Alice get the measuring count 0, then you see those two are really close. So Bob also has this 85% probability getting 0. And what if Alice measure 1? Well, these two things looks far away, but remember, this is not block sphere, and we really don't care about phase here, so we can get a minus sign. So this state is really this state, and they are really close. And that's really close to the Bob state here. So that's also 85% probability to get a minus 1, 1. Okay? And so that's 0, 1. And about 1, 0. Okay, it should. Okay. So Alice has this blue thing, and Bob's 0 is this thing. Heading back. I should not. Too late. Anyway, yeah. Yeah. So Alice is doing this, and Bob is doing this, and once again you see that really close. So you have pi over 8 here and pi over 8 here. And finally, the magical 1, 1, 1. So Alice doing this 1 and Bob doing this. Okay. Bob doing this. Now you see that they are mismatched, right? So when Alice doing this, okay, just in time. So Alice measure in this basis, 0, 1 basis, and Alice get 0, and should output A equal to 0, and then with high probability, then Alice get 0, then she will project Bob's state into 0. But Bob measuring this slightly off basis, then Bob has high probability to get this outcome. But on this outcome, Bob will say B equal to 1. And on the other hand, if Alice get A equal to 1 here, so okay, Alice get 1 outcome, then high probability Bob get this B equal to 0, right? Because Bob don't have dashed line here. So this is when Bob output B equals 0. Okay. So you see that we set up this nicely, so that just when xy equal to 1, 1, and Alice and Bob will have this high anti-correlation, where they have 85% probability of outputting A not equal to B. Okay. So that's how the quantum strategy works. And you see that although if Alice and Bob, when they measure in the same basis, they basically get classical randomness. But if you have this weird, slightly mismatched basis, you are able to get this interesting, weird quantum correlation, where you win this CSH game with 85% probability. more than a 75% probability you can do with classical correlation. Okay, for Austrian, otherwise we are just on time. Okay, people will like this picture, so I'll show this more. Anyway, yeah, so hopefully I can grade the midterm by Thursday and have midterm review and a little more on Thursday.